The three basic types of failures are as follows. The first one, failure by elastic deflection. Number two, failure by general yielding. Number three, failure by fracture. So these are the three basic types of failures. In applications like transmission shaft, the meshing of the teeth of the gears affected and shaft cannot perform its function properly. In this case, the shaft is said to have failed due to elastic deflection. Here you have a shaft on which a gear wheel is mounted, and it has to transfer power and motion from this gear wheel to another gear wheel, through which the output shaft has to be rotated. So when the shaft at the bottom is gets deflected, and it cannot have the contact between the upper one, and hence the shaft under the elastic deflection has failed to transmit the power as well as motion. So next, components made of ductile materials like steel lose their engineering usefulness due to large amount of plastic deformation. This type of failure is known as failure by yielding. Next, components made of brittle materials like cast iron fail because of sudden fracture without any plastic deformation. So there are two basic modes of gear tooth failure. Number one, breakage of tooth due to static and dynamic load, and next one is surface pitting. The surface of the gear tooth is covered with small pits resulting in rapid wear. So pitting is the surface fatigue failure. The components of the ball bearings, inner outer races fail due to fatigue cracks after certain number of revolutions. Sliding contact bearings fail due to corrosion, abrasive wear by foreign particles. So these are the various modes of failures for various components or elements. In the step 5, we are going to determine the dimensions of the element. Let us say here uh, a bar is subjected to axial tensile force of 5 kilonewton. This dimension, the dimension of the bar has to be determined. Mathematically, stress is equal to force upon the area, and the let us say the material of this bar has a allowable or working stress 80 mm, and force applied is 5 kilonewton, that is 5000 newton, divided by the cross sectional area, which is made of circular cross section. So pi by 4 d square is the area, from which you can find out the diameter. Diameter is 8.92 if we have corrected this 10 mm. So when a 5 kilonewton force has to be supported by a circular bar which is applied in the axial direction, tensile nature, the dimension, that is diameter of the bar, should be maximum of 10 mm. The permissible tensile stress for this rod is dividing the yield strength by factor of safety. Therefore, yield strength in this case is the criteria of the design. So here this 80 mm is the yield strength divided by the factor of safety, which is getting us the working or allowable stress. Next, if you take another bar which is also subjected to 5 kilonewton load, but it is acting as a different member. Here the bar, circular bar, is supported at both ends, and it is mounted with a gear wheel. So here the gear wheel is having combined force of its weight as well as the contact between the two gears together is known as 5 kilonewton. The radial force is applied is 5 kilonewton. So this force is acting at the midpoint of this bar. So therefore, here we have to consider the elastic deflection. For simply supported beam subjected to central point load of 5 kilonewton, the maximum deflection is PL cube by 48 EI, where P is the load applied and L is the length. Between the two bearings, the length is given as 100 plus 100, 200 mm, and E is the Young's modulus for the medium carbon steel, that is 2.07 into 10 to the power of 5, and I, the moment of inertia of area, is pi by 64 d power 4. Here the diameter required is 40 mm. Here also 5 kilonewton load is applied. In the earlier case also 5 kilonewton load is applied, but this 5 kilonewton load is applied in the axial direction, and that is tensile in nature, which resulted in the dimension as 10 mm, whereas this 5 kilonewton applied at the midpoint of the bar when bar is supported at its ends in simple support manner. The dimension is 40 mm. The requirement of the dimension in this case, where we consider the failure as elastic deflection. In the earlier case, it is yielding. Step 6. Design modification. The geometric dimensions of a machine element are modified from assembly and manufacturing considerations. For example, the transmission shaft illustrated is provided with the steps and shoulders for proper mounting of gear and bearings. The revised calculations are carried out for the operating capacity, margin of safety at critical cross sections, and resulting stresses, taking into consideration the effect of stress concentration. When these values differ from the desired values, the dimensions of the component has to be modified. So here is a shaft, just as shown in the earlier diagram, and at the supports for placement of the bearings, the shaft is slightly reduced in size. When it is reduced in size, here it becomes the case of stress concentration. When it is subjected to stress concentration, the stress at those points will become very high, and it must be taken into consideration. So therefore, if the failure is going to happen at that place, we need to modify the dimensions. These are the modifications of the design at the time of assembly and manufacturing. And finally, the step 7 is working drawing. The last step in the design of machine element is to prepare a working drawing, which includes dimensions, tolerances, surface finish grades, geometric tolerances, special production requirements like heat treatment, etc. The working drawing should be clear, concise, and complete. It must have enough views and cross sections to show all the details. The main view of the machine element should be shown in a position it is required to occupy in the service. Every dimension must be given. There should not be any scope for guesswork and necessity for scaling the drawing. All the dimensions that are important for the proper assembly and interchangeability must be provided with tolerances. Traditional design methods. So there are two traditional methods. One is design by craft evaluation, and second one is design by drawing. Bullock cart, rowing boat, plow, musical instrument. Such instruments are produced by craft evaluation process. The craftsmen do not prepare dimension drawing. They cannot offer adequate justification for the designs they make. These products are developed by trial and error over many centuries. Any modification in the product is very costly because the craftsman has to experiment with the product itself. Moreover, only one change at a time can be attempted. The complete reorganization of the product is very difficult. The essential information of the product, such as material, dimensions of the part, manufacturing methods, assembly techniques, are transmitted from place to place and time to time by two ways. Number one, with the product itself. Number two, exact memory of sequence of operations required to make the product. So these are the only two things. You may have product, and by looking at the product, you have to identify what could be the steps followed in order to make it to the final shape. Second one is the person who has done this should remember all the sequence of operations with his experience. He should pass on to his followers. There is no symbolic medium to record the design information of the product. With all these weaknesses, the craft evolution process has successfully developed some of the complex structures. The craft evolution method has become obsolete due to two reasons. Number one, it cannot adapt to the sudden changes in requirement. Number two, the product cannot be manufactured over a large scale. So with these two, the craft evolution has become obsolete. Now we follow design by drawing. The dimensions of the product are specified in advance to its manufacture. The complete manufacturing of the product can be subdivided into separate pieces which can be made by different people. One person is making one part, another person is making another part, and one is purchased from the market, and all these things are brought together and they are assembled. That's it. The division of work was not possible with the craft evolution, whereas here it is available. When the product is to be developed by trial and error, the process is carried out on the drawing board instead of shop floor. It is in the drawing room or in the design itself rather than while making it in the shop floor. The drawings of the products are modified and developed prior to the manufacture. In this method, much of the intellectual ability is taken away from the shop floor and it is assigned to the design engineers. Design synthesis. It is defined as the process of creating or selecting configurations, materials, shapes, dimensions for a product. It is a decision making process with the main objective is optimization. The basic difference between design analysis and design synthesis. In design analysis, the designer assumes a particular mechanism, a particular material, and a mode of failure for the component. With the help of these three, he is going to determine the dimensions of the product. Whereas in the design synthesis, is not going to make such assumptions. Here the designer selects the optimum configuration from number of alternative solutions. He decides the material for the component from number of alternative materials. He determines the optimum shape and dimensions on the basis of mathematical analysis. In design synthesis, the designer has to fix the objective. The objective can be minimum cost, minimum weight, or minimum volume, maximum reliability, or maximum life. The second step is the mathematical formulation of these objectives and requirements. And the final step is mathematical analysis of optimization and interpretation of the results. Use of standards in design. Standardization is defined as obligatory norms to which various characteristics of a product should conform. The characteristics include materials, dimensions, shape of the component, method of testing, method of marking, packing, and storing the product. The following standards are used in mechanical engineering design. Number one, standards for materials, their chemical composition, mechanical properties, heat treatment. For example, Indian standard IS 210 specifies 7 grades of grey cast iron designated as FG150, FG200, so on, FG400. The number indicates ultimate tensile strength in Newton per mm square. IS 1570 specifies the chemical composition of various grades of alloy steel. For example, alloy steel designated by 55 CR3 has 0.5 to 0.6% carbon. The average is 0.55. 0.55 into 100, 55. So this is the percentage of the carbon. Then it has 0.1 to 0.35 silicon and zero point 0.6 to 0.8 manganese, and the Cr stands for chromium. So it is chromium 0.6 to 0.8%. Standards for shapes and dimensions of commonly used machine elements. The machine elements includes bolts, screws, nuts, rivets, belts, chains, ball and roller bearings, wire ropes, keys, splines, etc. IS 2494 specifies the dimensions and shape of the cross section of endless V belts for power transmission. The dimensions of trapezoidal cross section of the belt, the width, height, included angle are specified in the standard. The dimensions of the rotary shaft oil seal is given in the IS 5129. These dimensions include inner and outer diameter and width of the oil seal unit. Standards for fits, tolerances, surface finish. The selection of type of fit for different application. Guide for selection of fits. The tolerances are upper and lower limits for various sizes of holes and shafts are specified on recommendations for limits and fits for engineering. IS 10719 explains the method for indicating the surface texture on technical drawings. The method of showing the geometrical tolerances is explained in IS 8000 on geometric tolerances on technical drawing. Next, standards for testing products. These standards, sometimes called codes, gives procedures to test products such as pressure vessels, boilers, crane and wire ropes, whereas the safety of the operator is of highest importance. The method of testing the pressure vessels is explained in IS 2825 code for unfired pressure vessels. Next, standards for engineering drawing. For example, there is a special publication by Bureau of Indian Standards, the engineering drawing practice for schools and colleges, which covers all the standards related to engineering drawing. There are two words, standard and code, which are often used in the standards. A standard is defined as set of specifications for parts, materials and processes. The objective of the standard is to reduce the variety and limit the number of items to a reasonable level. On the other hand, a code is defined as set of specifications for analysis, design, manufacture, testing, erection of the product. The purpose of the code is to achieve a specified level of safety. There are three types of standards used in the design office. Number one, company standards. They are used in a particular company or group of sister concerns. Number two, national standards such as Bureau of Indian Standards and DIN Germany, AISI or SAE in United States of America, BS British Standards in UK. Number three, international standards. These are prepared by International Standards Organization ISO. In design, the aim is to use as many standard components as possible for a given machine. The selection of standard parts in no way restricts the creative initiative of the designer, does not prevent him from finding better and more rational solutions.